Welcome back, everybody. It's Shucheng Yu. I'm sorry for my pronunciation.
Is correct.
From University of Science and Technology, Hefei, China. He will be talking about towards the 0-1 law for improvements to Dirichlet's approximation theorem.
Yeah. Thank you for having me, and happy birthday to Professor Dani. So today I'm going to talk about a result on improvements of the Dirichlet theorem, and this is a joint work with Dmitry Klemberg and Andreas Jobaxen. So just like every other talk in Diophantine approximation, let's start with the Dirichlet approximation theorem. And here, this is the version that we are having here is a higher dimensional version. And it says that if we fix mn to positive integers, and then for any n by n real matrix A, and then for any t greater than 1, there always exists a pair of integer vectors pq, where p is an m-dimensional vector and q is a non-zero n-dimensional vector, satisfying these two Diophantine inequalities. It says that up to this, so for the size of q up to t, the norm of q raised to the power n smaller or equal to t, you can always find a vector p such that this vector aq minus p is small, in the sense that the norm of it raised to the power m is smaller than 1 over t. And here the norm is the supernorm, and you're just taking the max of the absolute value of the coordinates. And in the classical setting of m equals n equals 1, this is the most classical Dirichlet theorem. It says that for the denominator up to t, you can always find a rational number, p over q, whose distance to a fixed real number x is smaller than 1 over qt. And here q is the denominator and t is any number greater than 1. So when t is large, you get this number is small, and you get a very good approximation to x. And this theorem has a quaternary, and usually people also call it's also called a Dirichlet theorem. It says that for any n by n real matrix A, there exist infinite many pairs of integers pq satisfying this inequality. The norm of aq minus p raised to the power m is smaller than the norm of q raised to the power minus n. And this is from the Dirichlet theorem to the quaternary is very simple, simply because whenever you have a solution to these two inequalities, because of the second inequality, you can always just bound 1 over t by the norm of q to the power minus n. And the fact that you have solutions for ot greater than 1 forces that here you must have infinite many such solutions. And these two theorems basically also represents two types of approximation. The second one is usually called asymptotic approximation. So it cares about the existence of infinite many solutions. So the conclusion is you have infinite many solutions to this Diophantine inequality. And then second, the first one is usually called uniform approximation, which is about to here the conclusion is for ot greater than 1, you can always find a solution to this inequality for these two inequalities, and usually you can weaken this condition for ot sufficiently large. So uniform approximation, it cares about the existence of solutions eventually always, whether this inequality eventually always have rational or integer solution integer solutions. And the natural question is for both of the two approximation is, can we improve this theorem in the sense that can we replace the right-hand side of those inequalities by some smaller number, meaning that we want a better quality for our approximation. And And so you can ask the same question for both type of approximations. And for the asymptotic theory, this question is very well answered by the classical Khintchine-Groshev theorem. So now I would just fix a psi to be my approximating function. It's always assumed to be continuous and decreasing, and it decays to 0 as t goes to infinity. And here's the usual notion of psi approximable. And n by n matrix A is called psi approximable if there exist infinite many integer solutions to this Diophantine inequality. And this inequality is just, it's the same inequality as we see from the coronary, except we change this particular number by psi of q to the power n. And you can easily check that the property of being psi approximable is preserved after adding a integer matrix. So for this reason, we can just to study those matrices, we can just restrict ourselves to this space of matrices with coefficient 9 in the unit interval. So R mod Z, it's a unit interval, and it's this is a n by n this is an mn dimensional torus, and you have a small advantage of that working on this space is because now you have a probability space. So then I would denote W psi to be the set of psi approximable real matrices, and then the Khintchine-Groshev theorem gives you a criterion on when the Lebesgue measure of this set W psi to have 0 or 1. So it says that if the sum of psi k is divergent, then this W psi set, this set is quite big in the sense that its Lebesgue measure is 1. And if the sum of psi k is convergent, then this set W psi is small in the sense that its Lebesgue measure is just 0. And this is a so-called 0-1 null. Because it gives you a criterion on when this set has Lebesgue measure 0 or 1. And for my talk today, so I care about the first type of approximation, which is a uniform approximation. And for this reason, let me give a definition, which is given by Kleinbock and Whitney in 2018. Here we say a real n by n matrix, real matrix A is psi Dirichlet if for all sufficient large t, there exist integer solutions PQ satisfying these two Diophantine inequalities. And again, in this case, comparing to the original Dirichlet theorem, I just changed the original 1 over t function by psi t. So originally it's 1 over t, but now I'm changing it to a general approximating function. And you can also check that the property of psi Dirichlet is preserved by adding a integer matrix. So again, I can just restrict myself to this torus, this n by n dimensional, mn dimensional torus, and I would denote di psi to be the set of psi Dirichlet real matrices. Okay, so the question that we are looking for is there a similar 0-1 null for the Lebesgue measure of the set di psi, analog to the Khintchine-Groshev theorem? And let's look at some examples that we know right now. If we look such psi 1t to be 1 over t, then Dirichlet's theorem, the original Dirichlet theorem, just tells you that the set di psi 1 is actually the whole matrix space. And this property is actually also actually goes back to Davenport and Smith in 1969, where they defines the notion of Dirichlet improvable vectors. And in here, we work in a slightly more general setting, which is about matrices. And in our terminology, this A is Dirichlet improvable if and only if A is C psi 1 Dirichlet for some real positive number C strictly smaller than 1. And then it was proved by Davenport and Smith that the set of Dirichlet improvable matrices is of 0 in the back measure. So in particular, we know that the back measure of di c psi 1 is 0 for any c smaller than 1. And if we compare this with the asymptotic theory, this is very different because from the Khintchine-Groshev theorem, we know that the set of psi approximable matrices is quite stable under adding a constant to the approximating function. Because if you go back to this theorem, if I add the constant to this function c, it doesn't change the convergence or divergence of this series. So in particular, it implies that the back measure of W psi is the same as the back measure of W c psi for any c greater than 0. But in this setting of uniform approximation, we see that a small change in the numerator. So originally it's 1 in the numerator. You get the whole space. Suddenly, if you just change this 1 by an arbitrary constant smaller than 1, could be arbitrarily close to 1, and this set suddenly becomes a measure 0 set. So there's a very dramatic drop in terms of the size of the set, and so which kind of indicates that this question is kind of more subtle, and then because of these two theorems, if we want to know some interesting cases where di psi could have like positive numeric measure, the functions that we are considering must be of this form. So it must eventually always that it must lies in between psi 1 and c psi 1, and here c is in any number smaller than 1, and for this reason, the approximating function that we have to consider must be of this form. So it's 1 over t. It's the original psi 1 function, but then I have to subtract something, and 1 minus at, and this at is a small function, and its value lies in between 0, 1, and the point is we have this at must decays to 0 as t goes to infinity. Otherwise, if at decays to some positive number, then eventually always this psi t would smaller than c psi 1 for some c smaller than 1. So, and then by the Davenport Smith, we know that if in that case di psi would have 0 in the back measure. So for the remaining of the talk, we will always just consider this kind of approximating functions. It's always of this form, 1 minus at over t, and at
excuse me,
decays. Yes.
Shucheng, question.
Yes.
I don't understand why at has to go to 0. Suppose at goes to some constant c along a very sparse sequence. Couldn't that still be?
But it's I forgot to say. Actually, we also eventually I would also assume this is some. Actually, we actually assume that this is decreasing.
Okay, so it also makes sense to ask sort of.
Yeah, it would. I think yes.
AT varying,
yeah.
like Diophantine analog.
Yeah, that's true. But for this talk, I would also always assume that AT would be decreasing. So, so the interesting case would just be AT decaying to 0. Yeah, that's yes. I think that's an interesting question for general AT without the monotonicity condition.
Okay,
but for this talk, it's always assumed to be decreasing. Thank you. Okay, so, and then here's some heuristics. So if this function AT decays fast, in the sense, so now our approximating function, so AT might be like close to 0, and then this approximating function which is closer to this 1 over t function. And then because we know that di psi 1 is the full space, so in this case, we expect that di psi to have large numeric measure. On the other hand, if this function at decays slowly, and then this psi t might be close to some c psi 1 function for some c smaller than 1, and then in this case, we expect the set di psi to have small numeric measure. And And also, there's another known case that this was proved by Kleinberg and Wadney in the same paper where they defined this Dirichlet this property. So here they deal with the one-dimensional case. So when here m equals n equals 1, and again assume psi t to be of this form, 1 minus at over t, and it's continuous and decreasing. And also, yeah, here we assume at is decreasing. And then the theorem says that if this series involving ak, so a is this function here, is convergent, then the set di psi has Lebesgue measure 1. And here the terms is k inverse times ak times log 1 over ak. And then if the same series is divergent, then di psi has Lebesgue measure 0. And so this condition is a bit more complicated than the Khintchine theorem, but still it's a it's an explicit condition, and it's a perfect 0-1-0 for determining the Lebesgue measure of the set di psi. And here's an example. If I take at to be this log function, so at equals log t to the power minus c. C is some positive number. Or equivalently, psi t is 1 minus log t to the power minus c over t. Then just some simple calculation, you will see that if this exponent c is greater than 1, then this series would be convergent, and then their theorem tells you that this di psi set has Lebesgue measure 1, and if this exponent is greater than 0 and smaller equal to 1, then this series will be divergent, and then the set di psi would have Lebesgue measure 0. And the proof uses continued fractions, but right now we don't know if it's applicable to higher dimensions. So there's some limitations for their proof. And then the result that I want to present today is a higher dimensional analog of this theorem, but we prove a weaker theorem. It's not a perfect 0-1-0, but we proved a partial 0-1. So now we're back to the general dimensions, and I will fix mn to be two two positive integers, and I will set d equals n plus n, and alpha, beta are the two quadratic functions in this number d. So alpha equals d squared plus d minus 4 over 2, and beta equals d squared minus d over 2. And then again, we assume we take our approximating function to be of this form, 1 minus at over t, and it's continuous decreasing. And again, this at function would be assumed to be decreasing. Then the theorem says that if this series involving the function at is convergent, then the di psi the set of di psi has Lebesgue measure 1. And then if this and then here the terms is k inverse times ak to the power alpha and times log of 1 minus 1 over ak raised to the power beta, and alpha beta are the two quadratic functions. And then if the same series is divergent, but then now we have to assume something extra, which I call this star condition. If these two conditions are both satisfied, then we can conclude that the set of di psi has 0 Lebesgue measure. And here the star condition is this kind of complicated lim-inf condition. It says that the lim-inf of this quotient equals 0, but we know that when m equals n equals 1, because of the theorem of Kleinberg and Wadney, this star condition is not needed. But for us, we have to assume this condition. And so what does this condition really say? If you look at this condition, if you first look at the denominator, the terms here are actually the same as the terms showing up in the series. But we raised. I'm sorry. So but then we are not taking the whole series, but we only take the partial sum. So the sum is sum of k and up to t. And then we also take another copy of it. So we raise this partial sum to power 2. And in the numerator, it's almost the original partial sum, except that we add a small nocturne. So the exponent of this nocturne here changes from beta to beta plus 1. So we add a nocturne to the to this term here. So this condition basically, and then we want this quotient of these two partial sums, the nim inf of this quotient, the quotient of these two partial sums equals 0. So we know that when we are under the condition that this series is diverges. So this condition basically says that it's only when this series diverges very slowly, this condition could fail. It's like, it's only when this series diverges super slowly, and then the impact of adding this small nocturne exceeds the impact of adding this whole copy of this partial sum, that this numerator would diverge faster than the denominator. And that's the case where this condition could be a problem for us. But if this series diverges at certain speed, then this start condition would always be satisfied, and then we don't have a problem. And we will see an example later. Yes, here's an example. So again, if I take this function at to be this power function of knock t, so knock t to the power minus c, or equivalent in psi t is 1 minus knock t to the power minus c over t, then just like in the one-dimensional case, just some simple calculation tells you that if this exponent c is greater than 1 over alpha, then the set of di psi has 4 Lebesgue measure. And if this exponent is smaller or equal to 1 over alpha, then this set of di psi has 0 Lebesgue measure. So for this particular example, our theorem tells you everything. For all the possible cases of the exponent, we know when the set has when the set of di psi has 0 on the or 1 or 4 Lebesgue measure. It's only when and also the critical case for this first example is when the exponent equals 1 over alpha, and it's only when you zoom in at this critical case. So now I take my function at to be, okay, so still the power function of knock t, so knock t, but then with this critical exponent, knock t to the power minus 1 over alpha, but then I add this smaller term, knock t to the power minus c. And then for this particular example, if you try to apply the theorem, and you can see that if this exponent c is greater than beta plus 1 over alpha, then this series will be convergent, and the theorem tells you that di psi has 4 Lebesgue measure. And then if this exponent is smaller than beta over alpha, then this series is divergent, and also the start condition, the quotient, it would also be 0. Then the theorem tells you that di psi has 0 Lebesgue measure. So, but then there's a gap for this example, is when the exponent lies in between these two numbers, beta over alpha and beta plus 1 over alpha. And the theorem for those cases, our theorem doesn't tell us any information on this on the Lebesgue measure of the set of di psi. But then we know that when for the one-dimensional case, because of the theorem of Kleinberg and Wadnik, we know that even for C in this range, the Lebesgue measure of di psi is also 0, and that's also what we expect in the general dimension. But right now, because we cannot remove this start condition, and for general for higher dimensions, for this example, our theorem only tell us about this partial range. It's not and we don't know anything about this range. Okay, so that's the theorem, and now let me say some words about the proof. As I said, so the one-dimensional case uses the continued fractions, but in higher dimensions, we don't have that.
Can I ask one more
yes.
question?
Yes.
In the main theorem, it's only about the sup norm. I mean, do you know anything about other norms, or is it just about sup norm?
Yeah. You could change the sup norm to any weighted norms, and the same result holds. So you go back to the definition. You can change it to any two fixed weighted norms, and then you can still have the same result.
What's a weighted norm? What do you mean by a weighted norm?
So weights is just alpha 1 to alpha m, and then sum of them is equals 1, and then the norm would just be you take the max of xi raised to the if I'm correct, 1 over alpha I, and you can consider this kind of norms, and this example would be the case when alpha equals the theorem that I'm considering would be those examples, those particular examples, but the same you can handle this general weighted norms. The proof could actually you don't pretty much it's essentially the same question in this uniform approximation. We don't need much extra work to prove this theorem, but I guess I didn't mention it here. But for other norms that, if you like Euclidean norm or other norms that we don't have result on those norms, and that would be very different, I think. Okay, so the proof, instead of using the continued fractions, we use homogeneous dynamics. We would translate this question into a dynamical problem and then try to solve this dynamical problem. So now let me introduce some setting. Again, I would set, so this D would be n plus n, and my homogeneous space X will be SLDR mod SLDC. It's a space of covalent one lattices in RD. And so here's a parameterization. So whenever you have an element in this quotient space G gamma, I can identify it with this unimodular lattice G acting on ZD. And then on this homogeneous space, you have a unique G invariant probability measure, which essentially comes from the Haar measure of this Lie group SODR. And then because X is this quotient space, the group G acts naturally on this homogeneous space X via just the left regular action. And the reason that this homogeneous space is related to Diophantine approximation is because the metric space that we care about naturally embeds in this bigger homogeneous space. So here's the embedding. Whenever you have given a n by n real matrix inside this space A, I can attach a unimodular lattice, and how do I do it? I consider this bigger D by D matrix, and so here actually it's a D by D unipotent matrix. Here on the top left is the n by n identity matrix, and here is n by n identity matrix, and here's just a 0, and I put this matrix A to the top right corner of this bigger matrix, and then I take lambda A to be the lattice represented by this unipotent matrix. And with this embedding, this torus naturally embeds and naturally identified with the submanifold, which I called Y, inside this bigger inside this bigger space X. And on this manifold, because it's homomorphic to this torus, it naturally has a the back measure. I just push the back measure here to the back measure of this torus Y. And so now we're in a situation where we have this bigger homogeneous space, and then there's a Haar measure on this space mu. But then what we care is this smaller torus Y, and which also has the back measure. So we will eventually restrict ourselves to this smaller set, but we have to work on this bigger homogeneous space. So we will have to work with respect to these two measures simultaneously: the Haar measure from the Lie group, and then the back measure from the torus. Okay, so that's the setting, and unsurprisingly, that the starting point of this everything is the Dani correspondence. So Dani correspondence basically it's a bridge in homogeneous dynamics. It kind of relates Diophantine properties of some matrices or vectors or numbers in terms of some dynamical properties of some orbits in the homogeneous space. And in our particular setting, the Dani correspondence tells us that there exists a continuous and decreasing function R, which is also positive, which is uniquely determined by the function psi t. And here we only consider this type of approximating function 1 minus AT over T, such that a matrix is not psi-Dirichlet if and only if this orbit GS lambda A hits the set KRS for an unbounded set of S, S greater than 0. And here GS is this diagonal one parameter diagonal subgroup. The first diagonal entry is e to the S over n, and then the last n diagonal entry is e to the minus S over n. And the set KR is a set of lattices which intersect this cube trivially. So basically we are in a situation where you have this continuous flow, and you also have a continuous family of shrinking targets. In our case, actually those sets shrinks, and then we're now looking at the conditions on when for generic lambda A, the set GS, this flow GS lambda A would hit this continuous family of shrinking targets for an unbounded set of S. And so basically we have reduced this question to a problem called shrinking target problem. And here this set KRs are defined is this set of lattices avoiding those cubes. And in our situation, this RS function would eventually decay to 0. So RS would be some positive number, but eventually as S goes to infinity, it would eventually decay to 0. So this cube, as R close to 0, those cube would be close to the double unit cube minus 1, 1 raised to the power D. So it's kind of a big cube, and not many lattices would avoid this cube. And so this is kind of a strong condition, and this set is a small set. And later we will see that this is actually some compact set sitting in our homogeneous space. And also it's part of the Dani correspondence that it's just some simple change of variable. You can show that this series, the convergence or divergence of this series involving the function A, so A is this function in our approximating function, is equivalent to the divergence or convergence of this series involving this R function. And then the term here is, and here this alpha beta are the two quadratic functions that we see from our theorem. And then so in other words, we have, so because of this, if you just rephrase this equivalence condition, we have, because here it's like the property A not being psi Dirichlet, so we are looking at the di psi complement. And then this condition just reduces to this lim-sup set. And eventually, so this equivalence condition just is equivalent to saying that the set di psi complement equals this lim-sup set T minus S KRS. But because we are only looking at this lattices from the torus, from this small torus, we are not looking at lattices from the whole ambient homogeneous space. We have to also take this intersection. So it's not so standard. We usually, for shrinking targets, you just care about the lim-sup set in the ambient homogeneous space. But here we have to take this extra intersection with this small torus. And so the question now just reduces to estimating the measure of this lim-sup set. There's still a small problem because this is a continuous lim-sup set. We want to discretize it because we know how to estimate the measure of a discrete lim-sup set. So how do we discretize it? We just define a set, this thickening set BK. It will just be the thickening of our shrinking targets along the diagonal flow up to the unit time. And you can easily see that the condition that GK lambda hits BK if and only if you have some GS lambda hits KRS for some S9 in between K and K plus 1. So because of this condition, this continuous lim-sup set just becomes this discrete lim-sup set. And now we just want to estimate, estimate or compute the measure of this lim-sup set. And for this, we can apply the Borel-Cantelli lemma, which I guess most of you must be very familiar with. So here X nu is a probability space, and if we are given a sequence of measurable sets or a sequence of events AK, then the convergence case of the Borel-Cantelli lemma says that if some of the measure is convergent, then this lim-sup set is measure zero, has measure zero, and it's a very this lemma is very easy to prove. And then we also have this divergence case, which is a bit more subtle. So first, because of the convergence theorem, in order to have this measure to be positive, we must have the sum of the measure to be divergent. But usually this is not enough. We also usually need to assume some independence conditions for those events. Okay, so here I will introduce this what I call quasi-independence condition, and it's actually more precisely should be called quasi-independence on average. So here we have this. It says that the lim inf of this quotient equals 0, and then in the numerator, so we want a dependence, and if those events AK are really dependent, then we know that the difference of this in this numerator would just be strictly 0, but that would be too strong in most of the dynamical systems. So now here we use some weaker condition. We just want this difference to be small, and then and small on average, and which means that we are taking this this double sum here. Ij runs through all the integers between k1 and k2, and then in the numerator it's sum of the measures square. I want the numerator to be small compared to the denominator, so I want to name the lim inf of this quotient equals 0 as k2 goes to infinity, and then for some k1, positive integer k1. Once you have, so essentially this condition says, essentially it just says this numerator, this double sum is little o of sum of the measure ai squared, k1 to k2. And once you have this quadratic independence condition, together with this divergence sum condition, then you can show that the measure of the limsup set is 4. It has four measure. And we will apply these two lemmas to study the set that we care about, the di psi complement, because this is just a limsup set. Okay, so again, just a recap of the Borel-Cantelli lemma, because we know that our di psi complement is just this limsup set. Then Borel-Cantelli lemma says that if the sum of the back measure of those intersection is convergent, then di psi complement has the back measure 0. And if some of those measure is divergent, and also if those events satisfy the quadratic independence condition, then this set has 4 back measure. So we would need to use this criterion. But then the first step is because in our theorem, it's not those series showing up. It's actually the series involving our approximating function. So we have to restate the convergence or divergence of this series, this sum of the back measures, in terms of our approximating function, and that's the theorem. The first theorem towards the main theorem. It says that actually the convergence of this sum of the measure is equivalent to the convergence of the series involving AK, and this is exactly the series showing up in our original theorem. So in particular, if you have this equivalence, you can already prove the convergence case, because if we have the series to be convergent, and because of this equivalence, we know that some of this back measure is convergent, and then by the Borel-Cantelli lemma, we know di psi complement has 0 in the back measure, or in other words, the set of psi Dirichlet matrices has 4 in the back measure. Okay, so to prove this theorem, we have to use 2 steps. The first step is we will need to estimate the Haar measure of our shrinking target. So BK is some set in the homogeneous space. So the first step is to estimate, compute the Haar measure of this set, and then, but that's not really the object that we care about. We care about this in the back measure. So, and then the second step is we have to relate this Haar measure in terms of the back measure of this intersection. So now the first step, we want to estimate the Haar measure of this shrinking target is BK. And remember, BK is this thickening of those set KR, and KR is a set of lattices avoiding this cube and intersecting this cube trivially. It has only 0 intersection. It has only 0 as an intersection point. And those sets KR are actually compact neighborhoods of the critical locus for the supreme norm in RD. And what are those critical locus? It's just you just take this R to be 0 here. It's a set of lattices intersecting this double unit cube trivially. And the reason why it's called a critical locus is because, first of all, the norm for the supreme norm are just the cubes. And then if you have a small cube, and it's relatively easy for a lattice to having no non-zero points inside it. So it's easy for a lattice to avoid this small cube. So you would have kind of a lot of lattices satisfying this condition. But as you enlarge your cube, it will become more and more difficult for your lattice to avoid this cube, and there will be one critical point where that's the exact moment that you can still have lattices avoiding the cube, as long as you enlarge this cube a little bit. Suddenly you have no lattices satisfying this property, and this moment is exactly when the cube is this double unit cube. And that's why it's called the critical locus for the supernorm. And then so the sets that we care about are some neighborhoods of the set K0, and for K0 we actually have a very, very precise description, which is given by Hajos. It says that if you let U to be the subgroup of upper triangular unipotent matrices in SODR, and then let W to be the subgroup of permutations, then the set of critical locus, it's exactly all the lattices represented by those upper triangular unipotents, and then you just permute all these lattices, and that's all you get for those critical locus. So in particular, we know that this is a singular set in our homogeneous space. In the case when D equals 2, this set is just this union of these two circles, and this lower upper triangular unipotent, where X is from 0 to 1. So you just get these two circles. And our set will be some neighborhood of this circle. So some compact neighborhood of this circle. Maybe this will be the KR. And we wonder, so in particular, we know that as R goes to 0, the KR would approach this singular set, and in particular, it has the back measure, the Haar measure of those sets would decay to 0 as R goes to 0. But for us, we need a more precise asymptotic formula, and here's this. We proved an exact asymptotic formula for the Haar measure of this set KR up to a constant. So here, let alpha beta to be these two quadratic numbers in D, and then we showed that the Haar measure of KR up to a constant equals R times R raised to the power alpha plus 1 times log 1 over R raised to the power beta. And here, as R goes to 0, so at least now we get the asymptotic formula for this set KR, but we need a formula for this thickening. And here's for the proof. It's kind of it's actually quite complicated, but in very brief words, what I can say is, so up to permutations, because we know that, so a lattice inside this set KR, because we know that, so this is close to K0, it's a neighborhood of K0. So in particular, we know that this GZD, this lattice is close to some matrix lattice represented by some unipotent matrix. So in particular, we know that if you choose the representative correctly, you will have a representative G whose diagonal entry is close to 1, and then those off diagonal entry, if product of these two, Gij times Gji, would be 0, because here for the unipotence there would be 1, 0. So more precisely, you can show that actually for a lattice inside KR, which roughly means that the diagonal entry is close to 1 up to R, and then for each of those diagonal entry, it gives you a contribution of R. You just do the simple integration, you get a copy of R, and there are d-1 such copies. There are d diagonal entry, but because of because of the determine one condition, so you have to remove one entry, so you get d-1 copies. And then for each pair of the symmetric off-diagonal entries, Gij and Gji, it satisfies that their product is small in the sense that it's bounded by R, and also each of them could be relatively large. They are only just bounded by 1. And then you just do a simple calculation, so you get this kind of region. So that's 1, 1, but this curve is like xy bounded by R. And then you just a simple calculation for the area. For this area, you will see that this area is basically is R times the log 1 of R. And there are this many copies, and then you just combine, you put everything together, you get R times R raised to the power d-1, and then times R log 1 of R raised to this power, and then that's exactly tells you the, it gives you the exactly the asymptotic formula that we have here. Okay, so, and with this asymptotic formula for the set KR, and then it's not difficult to see that how much of this thickening is roughly R to the power alpha and times log 1 over R raised to the beta. It's here, it's like before we have maybe like that might be the set KR, and then we have a thickening along one direction, and then it reduces, kills one exponent for this R. So that's why originally it's alpha plus 1, but now here we get just R raised to the power alpha. And then because of this corollaries, then you can easily show that the sum of the back measure, how much of the shrinking targets, the convergence of this series is the same as convergence of this series involving RK. And here RK, not K, it's just the same thing here. And then here we have but then we still have this first equivalence, which is from Dani correspondence. It relates the series involving R function with the series that we saw originally in the theorem. So now we have shown this equivalence, and that's the first step. Now we have computed the Haar measure, and then we have shown the equivalence of these two series. And then for the second step, we have to relate the back measure of this intersection with our Haar measure, because this is really the object that we care. It's not the Haar measure that we care. It's the back measure we care. And so what is this the back measure? So we are in a situation where you have this torus Y. Remember, Y is this torus homomorphic to the metric space, and then it was act by this diagonal flow GK. So it will have some GKY, and it's well known that this Y is actually the expanding holosphere of this diagonal flow, and which means that this translate GKY would actually eventually equidistributes on the space. And in terms of measure, it just says that the push forward of the back measure approaches to the Haar as K goes to infinity. And this back measure, this intersection here is exactly the push forward measure evaluated at the set BK. So to relate this Haar measure with this back measure, we just apply this equidistribution theorem. But because the set here, we are working with the shrinking targets problems, the set BK actually shrinks. So we have to use an effective version of this theorem. And this is the theorem is due to Kleinberg and Margulis. It says formally it says that there exists some positive constant delta, and then for any smooth test function, and for any k great positive integer k, and if you consider this this integral over y, So this integral is exactly the push forward Lebesgue evaluate at f. This equals the space average of the test function and plus an error. And here SF is some Sobolev norm. And for us, this Lebesgue measure is exactly this integral, except with this smooth function replaced by this indicator function. So we would have to take this for the application. We would take fk this to be some smooth approximating function approximating this indicator function. And just to summarize things, if you apply this effective distribution, you will see that this Lebesgue measure is just this integral, and then because fk is the approximating function of this indicator function, they are close to this integral is close to this integral with this indicator function replaced by fk. And then for this step, we apply the effective distribution. This integral is close to the space average of the test function, and then again, this test function is close to the Haar measure of the set bk. If you make all this approximation precise, then you can show that actually the convergence of this theorem, the convergence of some of those Lebesgue measure is the same as the convergence of some of the Haar measure. And this is, and then we already see from step 1, these two series, the convergence of these two series is equivalent. So in particular, we will see that the convergence of these two series is equivalent, which is written here. And that's exactly the first, the theorem that I presented. So this is the convergence case. And for the divergence case, knowing the effective distribution is not enough. You have to use the double mixing of two expanding holospheres to prove the quadratic independence condition. Because remember, to apply the divergence Borel-Cantelli lemma, we have to verify this quadratic independence condition, which roughly means we want the Lebesgue measure of this triple intersection is close to the product of these two Lebesgue measures. And for this, we applied this double mixing theorem, which is due to Kleinberg and Shi and Weiss from 2017. And here this particular version, this more precise version, is from Björklund and Bortnik. It says that for any two smooth test functions and for any two integers ij, if you consider this integral of this product, and it equals the product of these two Haar measure and then plus an arrow. And so what does this theorem say? It just basically says that the following thing. It says you have two large expanding holosphere ij big. It says that so both of them would be close to the homogeneous space because of the distribution theorem. And then this theorem basically tells you that if ij are actually, they are also well separated, then these two big holosphere, they're not just equidistributes themselves. They actually become they actually mix quite well. They are very close to being independent, and that's essentially what this equation says. But there's a problem with this theorem is that it only works well when ij are very far away from each other. If ij is close, these two orbits are kind of close to each other, so you don't have very good mixing. But anyway, if you just apply this double mixing theorem when ij is large, you can just doing everything, and I take fi, fj to be the smooth approximation functions to these two indicator functions. Eventually, you can show that this Lebesgue measure of this triple inner product is close to the product of these two Lebesgue measure. But then for the range when I minus j is small, we can only use this trivial estimate. So this is in the back measure, and then if you write this out, is this integral of these two indicator function. So what I do here, I just so Bj is a smaller set, Bi is a larger set. Here I'm assuming I is smaller or equal to j. So what I do is just I trivially bound the larger indicator function by 1. So then I get this integral, this integral over y, but of this single indicator function, and then this equals the back measure of this intersection. But here we lose something because we want this thing kind of to be close to the product, but not this single back measure. And that's exactly why we have to assume that technical star condition in our theorem to ensure with these two bounds to ensure this quasi-independence condition. Yeah, I think I'm a bit over time, I guess. I think I will just stop here. Thank you.
Any questions or comments?
So your results are on this torus that you called y. And what do you expect if you replace y by another another trajectory for the Hart spherical group and you put a measure on it? Do you expect the answer to be the same?
So I think, so what's missing, you can change this in the back measure by like a more synchronous measure on the torus. As long as you have this equal distribution theorem, I think you can apply the general machinery and then you can prove similar results with respect to that more synchronous measure. If, for example, you can just consider some, I guess there's a result of Sam Chow and Lei Yang, where they think in the case when d equals, I don't quite remember this. In the case when d equals 3, they have some effective distribution theorem replacing this torus by some straight lines on the torus. And then, so the measure would just be the back measure on this line, and then you can with their theorem you can actually prove kind of similar results, replacing this back measure by the back measure on this line. So as long as you have this analog of those equal distribution theorem, you can prove results for more general measures.
So if you're away from, say you take Lebesgue measure, but not on your torus y, but on some other Lebesgue measure multiplied by a function to get it to be a probability measure on some other orbit for the group, for the Hart spherical
other
group.
Orbit
Of the Hart spherical group, not this one.
That I'm not sure. We never thought about this, but I think I think you should be able to get something non-trivial as long as you have the necessary ingredients, like the necessary equal distribution or double mixing theorem. Then I don't know. We've never thought about this, but I'm guessing that you might have some, you could have some interest, some non-trivial results.
Questions or comments? If not, let's thank the speaker again.